Hi everyone, welcome back. In our last video, we finished up our discussion and exploration of electron configuration and orbital notation. Today I want to talk a little bit more about what happens to electrons when they gain energy, when electrons become excited. So let's take a look. We're going to talk about electrons and how they compare in their ground state versus their excited state. So the ground state for an electron is an electron that has the least or lowest amount of energy as possible. And this is considered the normal state for that electron. They usually don't like to hang on to a lot of extra energy that they don't normally have. So the ground state is the lowest energy. The excited state is the state that that electron is in when it gains energy and moves to a position of higher energy. As you know, we did some of our diagrams where we showed electrons in different energy levels. Okay, when that electron gains that energy, it moves to a temporary position of higher energy than the ground state, which means it will also be further from the nucleus. Okay, this isn't a stable electron at this point. That electron doesn't want to hang on to that energy, so it quickly returns back to the ground state. So when that electron becomes excited, okay, it's given energy in some way and causes it to jump to a higher orbit further from the nucleus. And this can happen in a number of ways. It can happen through collisions with other atoms, or it can gain energy in the form of light or photon or some type of energy absorption such as that. So when that electron gains that energy, okay, that excited atom is further from the nucleus, but like I said, it doesn't want to stay out there for very long. It doesn't want to hold on to the energy, and it falls back down to a lower energy state in about 100 millionth of a second. So not very long. But when it does that, it has to release that energy in some way. So depending how much energy it has and how much it then loses, okay, it will emit some form of radiation. And that radiation that the electron will then emit will match the amount of energy that the electron has to gain to move to that different energy level. So that orbital change that occurs for that electron in that atom has a specific amount of energy. And so the electromagnetic wave and that the electron gives off will match that amount. So oftentimes this is shown up as visible light. Okay, those electrons will give off visible light that we can actually observe and see and measure that amount of energy. So, and that varies depending on the type of atom. We'll see later on here that different atoms, different elements will have different amounts of energy that their electrons are allowed to gain and lose. So our changes in electron energy, what happens? Well, it must gain energy to transition to the excited state. So if we take a look at an electron in our diagram here, it moves from that inner energy level to the outer energy level. This is an atom of beryllium. Okay, it moved from the inner energy level. It gains energy, moves further from the nucleus into the excited state. Okay, so the electron gains energy and moves from the ground state to the excited state. The opposite then happens when it releases that energy. So that electron releases that energy in some wavelength, some radiation, okay, and so it moves back down to the ground state, okay, the ground state where it does not have energy, additional energy. Okay, so moving from the excited state to the ground state, that electron releases that energy. And light is given off. So if it's in the visible light spectrum, we're able to observe the light that is given off from that electron. So in this configuration, the electron is not excited. Okay, you have the electron in the ground state, A photon comes in, it's absorbed by the electron, and so now the atom is in an excited state because the electron has a higher than normal orbit. Okay, it's gained that energy, it's further from the nucleus, okay, and so it's a higher than normal orbit. Okay, so that electron moved to an outer energy level. When it loses that energy, okay, that the electron moves to a non-excited state. So it moves back down to the ground state and emits a photon of light. So let's take a look at a couple questions here. So compared to a sodium atom in the ground state, a sodium atom in the excited state must have what? Go ahead and pause the video, take a look, and we'll go through the answers here. All right, now that you've had a chance to take a look at this, okay, a sodium atom in the excited state must have, you got it, an electron with greater energy. Okay, for that electron to move to the excited state, it has to gain that energy. Okay, it's not a change in the number of electrons. Do not get that confused with it gaining or losing electrons. It does not gain or lose electrons. All that happens is we have the same number of electrons, but they just gain energy. Which electron configuration is possible for a nitrogen atom in the excited state? Go ahead and pause the video, see if you can figure out the answer. All right, now that you've had a chance to take a look at this, let's take a look at our answers here. We have a number of different electron configurations for nitrogen. But if you notice some of these answers, did they have the right number of electrons? Hopefully you checked that. Okay, and hopefully you picked B. B has the correct number of electrons. C and D do not have the correct number of electrons. And a standard electron configuration for nitrogen would be 1s2, 2s2, 2p3. But the other thing that we know about that electron configuration is each of those orbitals have higher energy. If you remember that from our notes from the last video, okay, each one has higher energy. So in our answer B, 1s2, 2s2, 2p2, and then 3s1, one of those electrons gained some energy and moved from the 2p orbital to the 3s orbital. Which electron transition represents a gain of energy? Well, if we're looking at an electron that moves from one energy shell to another energy shell, and it gained energy to do that, is it going to move further from the nucleus or is it going to move closer to the nucleus? Right, it's going to move further from the nucleus, therefore it needs to move from the second shell to the third shell. If we take a look at B, second to the first shell, that's moving closer to the nucleus. Same with third to the second and third to the first shell. So the farther from the nucleus, remember, the greater the amount of energy in that electron. So let's take a look at emission of energy. So all elements have a different energy level system that's unique to that particular element. Sodium's not going to have the same amount of energy exchange between levels as calcium would, okay, or as oxygen would, okay. All of those are going to have different energy levels when that electron changes from ground state to excited states. So, and this also depends on the amount of nuclear charge, right? What do we know about different nuclei in different elements, right? They have different numbers of protons and neutrons. Therefore, they're going to have different charges, and that's going to affect the amount of energy that's required for an electron to move to a higher energy state. So the amount of energy released when returning from an excited state to a ground state is different for each element. We know that some of the radiation that's emitted falls in the visible spectrum. Okay, the visible spectrum here has many different colors, as you already should know. Some of the energy has wavelengths in that visible light range. Some also emit ultraviolet, infrared, many different other wavelengths of electromagnetic radiation. However, these are the ones that we can see, right? We see these all the time. So different elements can then give us specific wavelengths of light that we can then observe and even identify some of these elements based on the wavelengths that we observe. So if the light emitted by an electron passes through a prism, so white light contains all the wavelengths. So we get a spectrum, much like we see when it rains outside and there's a rainbow. Okay, that white light from the sun travels through that rain, or that behaves like a prism and breaks apart those wavelengths of light. So that allows us to see the entire spectrum. So each of those colors is a different amount of energy, a different wavelength of light at a different energy level. So the atomic spectra for an element is then unique because we can identify that. We won't get an entire spectrum. Instead, we'll get specific wavelengths from each of those elements. So let's take a look at hydrogen. If we have hydrogen gas and light is emitted from that hydrogen gas, goes through a prism, it will break apart into a few different wavelengths. We can then observe those wavelengths and measure them to determine that it was hydrogen if we did not know. But in this case, hydrogen breaks up into those specific wavelengths. And we can actually observe that on film. Okay, here's a few of those wavelengths. So if we saw these wavelengths, we would know it was hydrogen. There's a few here closer to the ultraviolet spectrum as well. Okay, so this is known as a discrete emission spectrum, specific to hydrogen. Other elements are not going to have the same spectrum for us to observe as hydrogen. Again, each element has a different emission spectrum. Sodium, we'll take a look at a few here. Sodium has an emission spectrum that looks like this. So potassium will be different. Okay, there's a lot more emission spectrum for potassium that falls in the visible light range. Calcium, even greater number of emission that falls in the visible light spectrum. Copper, okay, if we get to do our lab, you'll see why copper appears like it does, due to the wavelengths that are emitted by copper. And then barium as well. All right, as you see here, none of these are the same. All of these elements have very different emission spectra. So the characteristic bright line spectrum of an element occurs when electrons do what? Right, they move from higher to lower energy level. Okay, when they emit that light, that's an emission of energy. That electron loses that energy and moves to a lower energy level. So that high to low movement of the electron releases that energy. So let's take a look at this. What two elements are present in the unknown spectra below? If you take a look at this bottom spectra, okay, we have an emission spectra, but we don't know what elements make up this unknown. We have to then match it up. We have a few options: lithium, hydrogen, and helium, and sodium, all with different emission spectrum. Go ahead and pause your video, see if you can figure out what elements are present in our unknown. All right, hopefully you've had a chance to look at that here. Let's take a look together. So we can see the spectrum lines up here with helium. Okay, but that spectrum, that wavelength, is not available or is not emitted by hydrogen, lithium, or sodium. The same is true for all the other spectrum lines for helium. Hydrogen, we see the same thing. The lines match up for hydrogen with the emission spectra for our unknown. Okay, so the answer was C, hydrogen and helium. All right, one more thing I want to talk about with regard to excited electrons and their ground state, a couple of phenomena that we are able to observe. One is called fluorescence. So some materials actually get excited not just by visible light, but also by ultraviolet light. Okay, and so these materials can also lose that energy and emit that ultraviolet light. Those materials are then referred to as fluorescent materials. Okay, they're excited by the ultraviolet light, but then emit visible light. So that's where we get some of the things that we see that fluoresce. So fluorescent lamps are an example of that. Primarily, fluorescent lamps are excited by collisions of those electrons with some type of gas usually located in that lamp. Could be mercury vapor. There's a bunch of different types of lamps, sodium, things like that. And then ultraviolet photons are then given off. So then there's a secondary excitation where those ultraviolet photons are absorbed by phosphorus. So if we take a look at the long tube fluorescent lamps that you might be familiar with, I think we even have some in the classroom. Ultraviolet energy is emitted in the lamp, but we don't see the ultraviolet light. Instead, what happens is there's another transfer of energy where that ultraviolet light goes into phosphorus, which is the white coating on that lamp. That ultraviolet photon is absorbed by that phosphorus, and then that phosphorus will then, when those electrons lose that energy, they then emit visible light that we're then able to observe. So remember, visible light from excited mercury vapor is also emitted. So there's more than one type of energy emission in fluorescent lamps. It's a multi-stage process. Phosphorescence is a really cool thing. You've probably seen it, didn't know it was called phosphorescence, but electrons get stuck in an excited state. So an electron gains that energy, moves to a higher energy level, okay, but it doesn't always lose that energy as fast as in other processes. So they get stuck in that higher energy level and they slowly start to lose that energy. And as they start to lose that energy, it still emits light, but it emits it over a longer period of time. So this causes a continuous glow. So when you see glow sticks and things like that, that's known as phosphorescence. That electron gained energy, but then it's taking a long period of time for it to lose that energy, and it allows it to glow for a long period of time. Okay, another example of that is bioluminescence. So oftentimes there are things in nature that naturally phosphoresce. So I hope that this has been a helpful video for you guys to understand where some of these sources of light come from and how they work and things like that. Fireworks, I'm a big fan of fireworks, aren't all the same color, right? And so you could actually try to figure out what elements are in those fireworks based on the colors that you see. So hopefully when you look around at sources of light from now on, you maybe think a little bit differently. Maybe you can figure out what some of those things are made of. So I hope this has been helpful for you guys. I will see you in the next one.